Okay, so we are now used to discussing the application of Euler's laws of motion to kinetics problems, which starts with our Newton's laws, which says F equals ma. In many instances, F is not a constant force, F itself is a function of time, and in many instances I am not interested in the instantaneous acceleration, I am interested in the effect of a particular time varying force acting over a certain period of time. I want to understand what change this force, the action of this force would have on the body of interest. Okay. So, that gives rise to a different approach, still based on Newton's laws of motion, but a different approach called impulse momentum. So, let us see if we can first understand the whole idea of impulse momentum formulation. So, we will start with our old Newton's law. I am going to write it as a simple scalar formulation, because just to illustrate the idea. Now, if f was a function of time, whatever be the function of time, then all it would say to start with is that a of t is also a function of time, that acceleration is also a function of time. Okay, so, f of t equals m times a of t, but like we said, I am not interested in the instantaneous accelerations. If f acts over a time interval, from an initial time ti to tf, a final time, then essentially let us say I have a force that kind of was 0 all the way to some initial time ti and became non-zero at some time tf. I want to understand the action of this force. Then the simplest way would be to write this in an integral formulation, okay. Now, knowing that a equals dv dt, this is the basic definition of acceleration, implies a dt can be replaced with the change in velocity. So, this means integral ti to tf f of t dt equals integral ti to tf m dv. If m is constant, this means integral ti to tf f of t dt equals m times v of f minus vi. V of f is simply the velocity at some time tf, and vi is velocity at some time ti. This right hand side here or left hand side here has a name. This is what is called impulse. The integral of a force which is time varying over a certain span of time is called impulse. So, impulse causes a change in momentum. So, the final momentum is m times vf, the initial momentum is m times vi. Okay. So, in many applications I will just be interested in this kind of a difference formulation. So, you remember this is a difference equation that tells me that for a given impulse the rate of change of momentum can be calculated, and let us see if we can use some applications of this. So, we will take this example here. A block of weight 160 newtons is on a inclined plane that is on this 3, 4, 5 triangle. There is a coefficient of friction which is got a coefficient of sliding friction, kinetic friction, that has a magnitude 1/3 for the coefficient acting on the bottom surface of the block, and the block is sliding up. So, there is a force here. The magnitude of the force is 160 plus 40 T is acting to push this block up. As T increases, you can see that the magnitude of this force F is increasing with time, and we are asked to find the magnitude and direction of the acceleration of the mass center as a function of time, and we are asked to find what is the time instant F at which the velocity is 16 meters per second. Okay. So, this is the prime candidate for our impulse momentum formulation, because the force is time varying, but I have to be a little careful here. This F, which is 160 plus 40 T, is not the only force acting on this block. So, in order to make sure I have a picture of all the forces acting on the block, I have to draw a free body diagram. There is a normal force, there is this force F, there is a force W, and this whole thing is on a 3, 4, 5 triangle. So, it is a firstly taking all normal forces normal to the plane is 0. Oh, by the way, I forgot, there is a friction force. Okay, just for the sake of clarity, I will call this as some P. Taking all perpendicular forces 0, what we find is that 3 W over 5 minus plus n equal to 0, which says n equals 3 W over 5. W itself is 160 newtons. So, n has a magnitude of 96 newtons. Now, taking all forces up the inclined plane as positive, P of t minus F, the friction force, minus mg sin alpha, which would be 4 W over 5 equals mass, which is W over g, times acceleration, and in this case if p is a function of time, the acceleration is also a function of time. So, let us plug some numbers in here. 160 plus 40 t minus, since we know the block is sliding, F equals mu times n. So, that is 1/3 of 96 that is 32 newtons. Minus 4W over 5 I am going to assume, like always, G is 10 meters per second squared, which puts the mass at 16 kilograms times A of t. So, I can quickly do this. 160 minus 32 minus 128 is simply, so this is A of t equals 40 t divided by 16, which is 5 t over 2, and this has units of meters per second squared. At some initial time t equal to 0. So, if I plot the acceleration versus time, at some initial time t equals 0, the acceleration is 0 and then it increases linearly. Equation of this line is 5 t over 2. That is not what we are asked to find. We are asked to find the time at which the block would acquire a velocity of 16 meters per second, given that at some initial time 0 seconds the velocity is also 0. So, this amounts to integrating a dt from 0 to some final time tf equals Vf minus Vi. We are given both Vf and Vi. Vf is 16 meters a second and Vi is 0. So, let us do that integration. 5 t over 2 dt 0 to some final time tf equals Vf minus Vi, which implies 5 over 4 t squared 0 to tf equals 16 minus 0, which implies 5 over 4 tf squared equals 16. Tf equals 164 over 5 seconds. So, this force acting on the block for about 3 seconds would get the block up the inclined plane to a velocity of 16 meters a second. So, essentially what we have done is calculated the force F of t, which in this case is the P of t minus mg sin alpha minus mu n. So, that whole thing is used to replace this f of t, and when we do that we are able to calculate the final change in the momentum m times Vf minus Vi. So, that gives you the final answer. We will take the next example problem in the next lecture.